Bene, buongiorno a tutti, condivido lo schermo. Schermo 2, condividi. Bene, buongiorno a tutti, un benvenuto a chi partecipa per la prima volta e invece bentornati a chi ha già avuto modo di seguire i precedenti webinar. Questo è infatti il terzo appuntamento che organizziamo assieme ad Aanderaa, ditta specializzata in strumenti oceanografici di cui noi siamo distributori in Italia. Oggi approfondiremo il tema della correntometria, con un occhio di riguardo alla strumentazione SeaGuard. Potete rivolgere le vostre domande nella chat e alla fine della presentazione risponderemo. Nei prossimi giorni riceverete un'email con i link per scaricare il materiale informativo. Nella stessa pagina ci saranno anche le informazioni e la documentazione dei webinar e le registrazioni dei webinar precedenti. Per chi non mi conoscesse, io sono Linda Croci, uno dei responsabili commerciali di WOTEC. Invece il nostro oratore è il dottor Anders Stenberg, ricercatore presso l'Università di Göteborg e Product Manager di Aanderaa. Hi Anders, good morning and welcome.
Hi Linda, and buongiorno a tutti. Thank you for letting me present at your series of webinars here. I will share my screen.
You. Okay.
You see my screen?
Yes, perfectly.
Okay. Yes. Thanks for joining, and I will present some possibilities with SeaGuard instruments. This is a type of instrument that we had for about 10 years now. They have been updated since we started with them, and there are many possibilities. Here we have two versions, but sensors are interchangeable in between the instruments. So if you have one SeaGuard instrument, you can use all the sensors that I will present here on the instrument, and it's plug and play. There are different depth ratings depending on the pressure cases and so, and we have from 300, 3000, 6000, and then we have a special version which is for Hadal, so it's down to 12,000 meters. We are involved in several really deep trench work projects at this time. So if we look first on the Doppler current profiling sensors, we have a Doppler current profiling sensor, which I have discussed in a previous webinar when we looked at selecting right methods for current and wave measurements. And what it has is it can measure currents then in multiple layers, of course, above the instrument, and in 150 cells, and you can program them to be at different sizes. You can go from 10 centimeters by having overlap of the cells to 10-meter cells. And the user can select whether to use broadband or narrowband. In the previous webinar we discussed this more in detail, and we could see that broadband is suitable to save power and gives you additional information on in the measurements. But if you're working from a platform that is moving a lot in the waves, for example, from a buoy or so, then narrowband seems to be a better, or we have seen it's a better option. You can measure surface currents with it, and every single ping that it sends out, it's compensated for tilt and movement, and the instrument can handle 35 degrees of tilt without any degradation of the data. And we have one feature which is unique, auto beam. If you have an object in one of the beams, it will automatically select. If you select that option, it will automatically select the free beams which are of better quality, where there is no objects. Often you have like a mooring chain or a float, something like that in one of the beams, and then it can automatically filter out that beam. You can use it upward looking or downward looking, and it has a wave option, has directional waves as an option, and that was also discussed in a previous webinar. You can add, for example, two profiling sensors to the same unit, and then double the range and still have high resolution and good quality of your data. This instrument is working with 600 kilohertz So typically the range, the profiling range is between 40 and 80 meters, depending on the conditions in the water. As I said, directional waves, it's an option, acoustic measured directional waves. One thing which is unique with all our sensors and instruments is that all the data are calculated on board and on the fly, so you don't need to do a lot of processing on your data. Everything is calculated automatically on the fly, and that also is an advantage if you want to transmit the data in real time, because it's much more prepared and compressed. Then the single point Doppler current sensor, it's measuring at 2 megahertz. It uses a double pulse, we call it Z pulse. It's sending out the signal horizontally, which gives you much better quality on your horizontal current measurements, but it cannot measure the vertical currents. And it can handle tilts up to 50 degrees and still measure correctly. It's automatically compensated for that. And we have seen in recent applications that it's a good correlation between the backscatter levels given by this sensor in a very well-defined volume and turbidity. So it can be used also to look at particle concentrations. And as with all our instruments, they are multi-parameter. You can add sensors. It's a plug and play. You switch off the power, you add the sensors and switch on the power, and then it's ready to measure with the new sensor. And that gives the advantage, for example, that you can use the instrument to log sensors on a string. Here you see a shorter string laid out on the deck between deployments. I will show you one or two more examples of that. And also these instruments can they accept sensors from other manufacturers as long as they have an analog output or a serial output. The instrument has can take 2 serial sensors and 4 analog sensors. And I want to point out here what we are releasing this year. It's a series of new sensors which are relevant to the SeaGuard. For example, turbidity, a new turbidity sensor which can be used on strings, for example, and with 0 to 2500 NTU range. A new conductivity sensor with a factor of 100 or factor of 10 better absolute accuracy, and some new versions of the oxygen optodes, for example, trace oxygen. And we have one software which is called real-time collector, which handles all our instruments and sensors. So you connect to this software, and then you are able to set up automatically. The software will recognize which sensor or instrument is connected, and you're able to set it up. And we also have features for real time, where you can transmit compressed data, and you can select which data to store on board, which data to transmit. So a very efficient way of sending data over in real time. And with the instrument comes powerful graphical software, which is included with the instrument, where you can make different 3D and 2D plots and line plots to have a good overview over the data and easily export them also into other formats if you need to do more processing of your data. Typically these instruments are used on moorings like this here, deep moorings, and we will see some examples of that. You can also have them in a bottom frame. This is typically used, for example, in port and harbor applications. If you want to measure directional waves, we recommend to have a bottom frame with a gimbal, because then to get good directional waves with the acoustics, the instrument needs to be stable and not moving. One feature of these instruments, of the SeaGuard instruments, is that you can put sensors in different logging intervals. This is a thing which can be practical. If you run sensors on the same instrument with significantly different type, for example, this is just an example, you can put pressure sensor in 2-second intervals if you want to detect small changes in the sea level, or if you want to detect small movements in the seafloor. I will show you some example of that. And then at the same time you can have a current sensor which automatically pings maybe 150 times over 10 minutes. You can have it working by itself on a 10-minute interval, and then at the same time maybe you want a longer interval for the waves, and then you can put that in a group with longer measurements. So you have three parallel groups with different logging intervals depending on what you would like to do and how advanced your experiment. You need to adapt your data for your experiment. So here are some examples of applications which I will come back to, but basically by having this you have a lot of possibilities of doing different types of measurements. And here you maybe notice I've included also a wind sensor, and this is because now in several projects and with several customers, they have a SeaGuard as a logger on a buoy, and the SeaGuard then logs the currents, surface currents with the Doppler current sensor, single point, and then below that the profiling sensor, and then it takes in an external compass to compensate for magnetic disturbances that you often have on a buoy, and then also a wind or a meteorological sensor which is connected by serial. So this is also a way to use this SeaGuard instrument, which is mainly then of course made for underwater applications. So I will show you some examples of how these instruments have been used. I already showed you this project in a previous presentation about currents, but now I will present to you some new data that we just analyzed at the university. And what we are looking here is effects of ships, mixing from ships, and how it affects the environment, both in terms of spreading pollution, in terms of gas exchange, atmosphere and water, in terms of mixing, in terms of so mixing up through the stratified layers. Erosion we don't look so much on, that has been studied abundantly in other studies. So here is examples from our field work last summer, where we, for example, to look at the movement of the halocline, we use small CTDs before and after the ships. Here is an electrical ferry that just passed and we're measuring behind. Here is a big ship that goes between Copenhagen and Oslo in Norway that we also measure behind. So we want to detect influence of ship and how the ship wake is spreading and how it affects the halocline. And so we deployed instruments here under the ship lanes. We had two Nortec instruments, one signature 500 and here a signature 1000 on a buoy. Below the signature 1000 we had a SeaGuard 2. A SeaGuard 2 instrument in its mooring frame, so deployed at about 35 meters below the surface and looking upwards, and then combined with the signature 1000. In this case we deployed under the ship lane, north-going ship lane through a strait here between Sweden and Denmark. And there is about 50 ships or 60 ships passing every day. And we have also ferries sailing about 1.5 to 2 kilometers here further north, back and forth here between Sweden and Denmark. One ferry every 20 minutes. And some of these are electrical. This one here, for example, is an electrical ferry that charges when it comes into shore. So we want to detect ships. We get the AIS data, how the ships are moving from automatic identification system, and with that we can see when they passed over our instruments and how it affected the mixing. So here is just a background plot. This is using the freely available software with the instruments, the 3D Studio software, where I just make a plot over a couple of days. This is just 3 days. We deploy the instruments for several weeks. And looking at different information here, for example, the vertical currents, we can see here is the north speed. This is a strait which is oriented mainly north-south. And we can see here, you don't see the scale, but we can see the different layers here and how currents are going during these 3 days. Here is the signal strength, the backscatter level from acoustic reflections from the profiler. And we can see very strong echoes here. This is fish. So we have big schools of fish, herring here, moving in the sound. It's a rich area for fishing. There is no trawling here, restrictions in that, so there's a lot of fish. And then one parameter which we looked a lot at to see mixing from ships is the standard deviation of the speed, of the horizontal speed. It is automatically calculated from the instrument. So after recovering the instrument in 1 or 2 hours, I made many of these plots and looked at the information and have a good overview over what happened during the deployment. In this case, the SeaGuard instrument also had a wave sensor on it and a pressure-based wave sensor, so it measured waves. You can see it in red here. Wave height was, in this case, for these days, maximum about 0.8 meters. We had salinity measurements in several levels. We had oxygen measurements in several levels. And here you see the tidal measurements, pressure, temperature, salinity, and here is the progressive vectors that show you the main currents here in different layers is north-south. So this is the direction of the strait. So if we look at this standard deviation of the horizontal speed, we want to see mixing and influences of ship. Can we detect the ships that are passing? Typically, if we make a 3D plot of it, we can see here going from the surface down to the bottom. Here is the time scale. That if these are influences of the ships, they go to different depths. We can see here it goes to about 10 meters below surface, then it levels off. Some of these influences only go more shallow. So we then start to, this is the same thing, a 2D plot just for 24 hours, and the standard deviation of the horizontal currents automatically calculated by the instrument and available directly at recovery. We see here we seem to have this mixing things from the standard deviation. Here we have a big school of fish, and here we cannot really do any of these calculations. It disturbs the calculations. So we only look into the periods where we have these things that seems to be coming from above. And if I correlate this with ship passages during these 24 hours, every single peak here correlates perfectly with a ship passing in the area. So these are names of ships passing. I don't expect you to see this in detail, but I also marked here how far away these ships were. And to our surprise, we could see ships, the ferries, for example, passing north of the instrument installation at 1800 meters, at 1500 meters. We could see these effects of these ships as well. So every single detection of such an anomaly in the horizontal currents, a turbulence, was what could be correlated exactly in time to a ship passage, except one actually. We suspect here that this ship did not have the AIS on, because that one we didn't see. If we then also look at the same thing, but directly from the signal strength, from the acoustic reflections, we see that ships that pass just straight over instruments or very close, they can be detected, and that's probably the bubbles from the ships that we see. So we could detect them, but only here the ships that pass within 200 to 300 meters or so. And in the next deployment that we will do this summer, instead of going out and doing a lot of CTD casts, which takes a lot of time and it's difficult to get a good coverage, we plan to deploy the same instrument with a string of sensors. This is a string that we have available from an observatory that we have been running for the past 10 years or so, and that we now have recovered. And then we will get the halocline automatically measured, because the string has oxygen and salinity sensors on it. And here is an example of such data from the fjord where we had the observatory. So then we will get both the mixing and how the ships affect the halocline, and if this mixing really goes below the halocline, and how the halocline moves up and down. So combination of acoustics and other sensors we discussed in the previous project here, and one combination where we have used this, where we combine sensors, which in a really useful way, was this project I showed to you in the previous presentation as well. That was combining turbidity with acoustic backscatter. Here is a project where we look at effects of trawlers passing in areas where they dumped chemical ammunition, and how trawlers resuspend the sediments, and how the fine particles from the sediments spread with the currents. Here we deployed two instruments like this with bottom weights and instrument in a frame with an acoustic release below and floats. This was at 200 meters depth. And we can see here all these peaks are completely related to trawlers. We have AIS data from the trawlers passing by, and here we see trawl tracks in the ammunition dump site where we have wrecks which were sunk full of mustard gas. And if we combine the turbidity measurements that we saw in the previous slide with the acoustic measurements, we can see we get a good idea of how high above the seafloor the particles are spreading from the trawlers. And so the turbidity kind of gives you a calibration point for your acoustics, because it's a better way of measuring mineralogenic particles in the water to use turbidity instead of the acoustic reflections. And by putting two turbidity sensors, for example, at different levels, you get an even better estimate of how much particles are resuspended from the trawlers. In this area, currents were not high enough to resuspend the sediments naturally, so it was just resuspension done by the trawlers passing by. Now I pass on a little bit to experiments or measurements done with a single point current sensors, still using the same SeaGuard instrument, still using multi-parameter possibilities. The thing is that with acoustic profilers it's very difficult or impossible. We have never managed to do it, to do any serious absolute referencing of the current measurements, because in a tow tank, which is the best method, we see here an example of that, the acoustic profilers will have a lot of reflections against the walls. It will be affected by this, and the water also sorry, in the tow tanks are often quite clear, and that also gives difficulties in getting good profiling measurements. But for the single point instruments, we have done a lot of, or our customers have done a lot of tow tank testing, and here is an example of that from China, in Tianjin, at the university in Tianjin, outside Beijing. And the results from that shows that the quality, they have tow tank tested many of our instruments, they do that routinely, that the quality of the data is really good of the SeaGuard measurements. And here we see the relation between the trolley speed, and which is the reference then, and the speed of that measures the SeaGuard instrument. And one thing that we try to do with all our sensors and instruments is to have methods for the customers or for the end users to test that everything is functioning correctly, that technically the instrument is functioning correctly before and after deployment. And here for the single point we have a test unit which you put on the head, and then you can see if the transducers are working well, and the tilt compensation and the compass is working as it should. So single point instruments have been used in many applications, and here we have one example. It will soon be, this was presented at the EGU meeting by Pierre-Henri. They deployed an instrument in the Marmara Sea, seismic active area, as you know, outside Turkey, outside Istanbul, close. And here there are a lot of earthquakes, and it was on a bottom lander frame. It was deployed, and after some time came an earthquake, and there was a turbidity current through a canyon, or a turbidity current was triggered by the earthquake. It came through the canyon, and the lander tipped over. And here the SeaGuard really gave a lot of useful information, both by the very sensitive pressure sensors that it have that can log at high frequency, simultaneously as the current sensor was giving tilt of the lander. It was giving how much particles was in the water, and then you also had the additional other measurements in parallel. And there was also quartz pressure sensors on board in this application, but they were not behaving as well as they had some damage, and they are orientation sensitive. So the SeaGuard was giving really good information about what happened after the earthquake and when the earthquake was triggered. And this is now being presented in a scientific paper, which is not yet published. And the way to measure, so that was an example of using pressure sensors to look at variations at the seafloor. And another application where this is done is in the offshore oil industry here from Norway, where many SeaGuards and many of these ultra-sensitive and very rugged pressure sensors are used to detect millimeter movements of the seafloor. This is surveys of the oil wells to be sure that they are not collapsing or increasing. So they need to have really high accuracy and high stability of the sensors. So normally 2 pressure sensors with different ranges are put on SeaGuard instruments, and then they place many around the oil wells. I think this customer has about 200 SeaGuards and instruments with dual pressure sensors. And so that was just to measure seafloor movements. Here is an application of Hawaii done by NOAA at Hawaii, where they look at conditions for deep water corals. These are growing at 200 to 300 meters in the Hawaiian area, and here they deployed the SeaGuard to look at conditions at the site here. It was placed here by an ROV, and it was supposed to be recovered after 1 year, but there was some issues with the ships and ship time, so they couldn't recover it. So they came back after 4 years, and then it turned out that the SeaGuard had recorded 1,014 days at 20-minute interval. And here are examples of some data from that. We can see in the lower pane here, we can see the signal strength, the acoustic signal strength from the instrument, how it goes from quite normally high in areas close to the bottom to very low values on the acoustic signal strength. And that is related to green here, which is higher currents. And these things happening here, they could then see and model that this is upwelling from deeper layers with much lower particle concentrations in the water. So but the turbidity here was not really giving any good estimate of that, but the backscatter did, and they could see how deep water with much lower particle concentration and much lower biological activity in it was upwelling occasionally. And this thing to correlate turbidity with backscatter, so turbidity measurements, which is an optical reflection, with acoustic backscatter from a higher frequency instrument like the single point Doppler current sensor. Experiments on that was done in German rivers, where the German Wasser- und Schifffahrtsamt, they use about 160 SeaGuard instruments with turbidity, salinity, and oxygen sensors and current sensors on them to measure continuously in the area where the big harbors are. Here is Emden, and there is also in the Elbe River where Hamburg is lying, one of the biggest harbors in Europe. And they use this data to model sediment transport and plan dredging activities. So, but one issue they had was that during longer deployments, turbidity sensors tend to get fouled and affected by biofouling or things floating in the water like algae or so, and eventually results will get biased or drift because of that. So they deployed, we looked into the correlation between acoustic backscatter data and turbidity data. Here on the upper panel here, you see turbidity variations quite high here, between 0 or a little above 0, but up to 1000 NTU. Oscillations here with the tides. You can see here at the lower panel here, east currents and north currents. So currents are going in and out of the area here, driven by the tides. And here we see the direction. It's completely tidally driven, and you see the speed here from low speed to about 130 or so maximum speed. And here at the lower panel here, you see the acoustic backscatter, where lower minus levels, it's lower levels. So if you correlate this, you get, if you put the optical measurements in turbidity in logarithmic scale here and compare it with the acoustics, you get a correlation which is quite okay, and which gives the possibility, because the acoustic sensors are not sensitive to biofouling, they can go for a very long time without any issues. So in this case, it gave the users here a good possibility to use data even after the optical sensor had some biofouling issues. And yes, and I want to show you also one example of where this acoustic backscatter could be used to look at relative particle changes over time. This is from OGS in Trieste, and I think there are some people on this presentation from OGS where they deploy at 1250 meters SeaGuard instrument during several years. It's still in the water as far as I know, and it measures salinity, temperature, oxygen and currents, and then you also get this, and turbidity, and then you also get this backscatter information from acoustic backscatter information from the sensor here. In this case, turbidity has not been working so well. After some time, some 1 month or so, the turbidity jumps up, it's noisy. We don't know exactly what is happening, because in the lab the sensor seems to work well. We have peaks, and yeah, it has not been working so well. Here is just a zoomed in picture of that. But if you look at the acoustic backscatter, we see a very consistent behavior with higher values this is at 1250 meters, with higher values after the spring bloom here in the spring. Next year you also have a peak or going up in the spring, and next year again, and next year again. We see these variations. We see that after instrument is recovered, data downloaded, and the instrument is redeployed, the values comes back to very similar values to what you had before, and that is always a good sign that there is no drift due to biofouling or drift in the signal over time. And you can see every time different colors here are different deployments and recoveries, that it comes back to the same readings after having downloaded the data. And finally, I want to show you some data from Antarctica, and here is just a comparison. The challenge here is that just to make long deployments, because water is very cold, and also water in the winter time here in the Antarctic winter time is very clear, very few particles in the water, so that's a challenge. And then another challenge is that the magnetic fields here are very weak, so it's difficult to it's questionable how well you can trust the directional data. Here it's measurements done by L'Océan in France, and that was done several years ago. It was 10 years ago. And here they have moorings. You can see moorings here with floats and sediment traps and different instruments. There are SeaGuard instruments on the moorings. There are also aquadopp instruments from Nortec on these moorings. And they were deployed typically for 1 year at a time. And but in some cases they could not recover because their ice conditions didn't permit that. So they had to stay down for a longer time period, about 14 to 15 months. And here I just plotted and compared some data from an aquadopp and the SeaGuard that was deployed and redeployed. So in this case, blue is the north component of the SeaGuard. This is over a 2-year or 26 months deployment period. First deployment period was about 12 months, second was about 14 months. And red is the aquadopp measuring, and as you can see, the aquadopp had a free sensor, and it was typically working for about 5 to 7 months. The SeaGuard instruments were always running. They had, in this case, 8 sensors on them, and so they were all the time delivering data and could handle the cold water. And there are some differences here in direction. The SeaGuard instruments, when being redeployed, we see that they don't change the direction. Here is a redeployment. So we think that the compass is, as far as we have seen, we have this solid state free axis compasses, and as far as we could see is that they work well also in this environment with low magnetic fields. And then finally some slides on another Antarctic deployment. This is a deployment which will last forever, because once the instruments are installed, they cannot be recovered. These are SeaGuard instruments installed and interconnected to each other, installed through the ice by drilling. So by drilling through 700 meters of ice with hot water, and then the instruments are installed through the hole, and after a week or so the hole freezes over and you can never recover them again. So these instruments here were installed about 10 years ago and have been working since that time, and they measure currents, single point currents, salinity, temperature, oxygen. And there was, in this case, 4 instruments on a string here going down. And what is studied here is this melting and freezing processes of the ice shelf here, and to see if the ice shelf is increasing or decreasing, and what type of circulations affects the increase or decrease of the ice shelf. And this is a project from University of Bergen, Svein Østerhus, who has been doing a lot of Antarctic research for the past 30 years or so. And to get real-time data is sent back by satellites, but that has been working on and off. It works. Batteries. It runs out of batteries for the transmission about 6 months every year, and then the instruments have been working all the time, and data are also stored here as a backup here on the surface of the ice. So with this, I would like to say thank you for listening, and I don't know if there was any questions in the chat. Linda, did you see that?
No questions. If somebody has to ask question, you can write in the chat. Se avete delle domande le potete scrivere nella chat. Potete anche poi scriverci un'email successivamente e le rivolgeremo ad Anders. No questions, Anders.
Okay,
So,
everything was clear? Yes.
yes, it seems.
Yes.
Ok, thank you very much. And grazie a tutti quanti per la partecipazione. E speriamo di avervi presto ospiti per il quarto e ultimo webinar. Speriamo poi successivamente di fare qualche attività dal vivo, siamo tutti un po' stanchi di fare webinar da remoto, seminari da remoto, dal vivo è tutto molto più bello e incisivo. Thank you, Anders. Hopefully we will see you in live person soon.
I hope so too. Grazie mille.
Thank you and see you.